So I guess this is our last lecture of the semester. I hope you've been able to learn at least something from these lectures. It's a new experience for all of us, so I'm sure improvements are always possible. Yeah. So we do have a full lecture ahead of us today, so I'll just keep going. And again, in the interest of making sure that I complete our lecture series today, I have written out today's lecture. So let's just get started. So today, so in the last class, what we did was I started discussing, that is lecture 41, I started discussing cyclic codes. And I mentioned to you that we are going to discuss cyclic codes from a transform domain point of view. And the connection was in terms of closed sets of frequencies. And an important theorem that we actually showed last time was that there is a one-to-one correspondence between cyclic codes on the one hand and sets of frequencies that are closed under conjugation on the other, and that is the null spectrum theorem which appears over here. Then we moved on to discussing the parameters of cyclic codes, and the block length is obvious. The two other parameters of interest are the dimension and the minimum distance. So the dimension, we proved a theorem which stated that the dimension of the code is the size of the complement of the null spectrum. In other words, you count how many frequencies there in the null spectrum, and n minus that amount is the dimension of the code. Okay, so the dimension is straightforward once you are given the null spectrum. So that leads us to the minimum distance, and the minimum distance in general it's tricky problem to estimate the minimum distance. What we did do is we said, well, let's consider a certain class of codes in which we structure the null spectrum to contain a consecutive string of d minus 1 frequencies. Then the minimum distance is greater than or equal to d, and this d, parameter d, is called the design distance. Often the minimum distance is equal to the design distance, but it could be larger. And the proof is via a theorem which we call the weight theorem, which said that if you have a vector whose with Hamming weight in the time domain, then that translates in the frequency domain to a linear recursion relationship amongst the transform coefficients, where the degree of the linear recursion is equal to the Hamming weight. So if W was the weight, then the degree of the linear recursion would actually be weight. Then after that, we discussed an example of BCH codes known as primitive binary BCH codes. I just want to make one comment before I come back to this. That is, in our last class we had a lecture in which I actually discussed a class of cyclic codes where you had the usual conditions, and then I put in the additional condition that you have a string of d minus 1 zeros. I just want to highlight that this class of codes is generally known as the class of BCH codes, and this parameter d is called the design distance of the BCH code. So I just wanted to make sure that you identify this class of code with the class of BCH codes. Okay. So now, that is the reason for reproducing a theorem which you saw in the last lecture. So anyway, coming back here, towards the end what we did was we looked at a particular example of BCH codes. In what way was it particular? Well, it was particular in two respects. First of all, it was binary, because in general BCH codes could also be non-binary, and in the second aspect was that the codes were primitive. That means the length is of the form 2 to the m minus 1. So primitive translates into this, and then now if you specify the null spectrum in terms of a consecutive string of frequencies, or mandating that the null spectrum contain a consecutive string of frequencies, then you haven't really nailed down the null spectrum exactly. So that leaves some uncertainty about the size of the null spectrum, and because of that it is hard to give a precise count for the dimension of the code. But in this particular case, that is in the case of binary BCH codes, and in particular we there was another thing that we did, which was particular, is that we set the parameter m0 to be 1. That is, the first frequency was set as equal to 1. Under these circumstances, you can actually say that, well, my dimension is given by this and this is my minimum distance, and this is often a pretty good estimate of the dimension. And these codes are very efficient. They are amongst the best known binary codes. So often if you require a binary code with large minimum distance, then this is a generic construction which might well cover your case. Alright, so these I will regard as the parameters of a T error correcting BCH code. So that concludes the summary of what we did last time. So now what I want to do is I want to actually say, well, as a second example, I am going to show that a class of codes. Now this class of codes is the most widespread class of code in use today. It is known as the Reed-Solomon code, and although from the way we have presented it here, it appears as an example of BCH codes, Reed-Solomon codes can be given an independent definition, and in fact were discovered independently. Okay. So this is just a unification that I am presenting here, in which I actually show that Reed-Solomon codes can be regarded as particular classes of BCH codes. So what's special about this, what's particular to this case is that here q is a power of prime, no surprises there, but n divides q minus 1, that is new. In other words, you are saying that the block length is less than q, less than or equal to q minus 1. Now what that means is that because n divides q minus 1, that means q minus 1 is a multiple of n, and therefore q is 1 plus a multiple of n, which means that q is 1 mod n. So the multiplicative order of q modulo n is 1. So that parameter little m that we have been using throughout in this case is just 1. So therefore m, the m that we have been talking about, ends up being just 1. So in particular, that means that in the case of Reed-Solomon codes, there is only one field to speak of, because remember, typically we had two fields. We had fq and then we had the field fq to the m sitting on top, but now in the current case this is equal to fq. So there are no two fields, there is just a single field in this particular case. Okay. So here is an example. Supposing q is 2 to the 4, n is 15, then m, and okay, so we know that m is 1. Now I am going to fix the parameter m0 to be 2 and d to be 5. So by this we are mandating that the BCH code contain, which is the Reed-Solomon code because it satisfies these conditions, that this Reed-Solomon code, the null spectrum is mandated to contain m0, m0 plus 1 through m0 plus d minus 2, which in this case means that it must contain the consecutive string of frequencies 2, 3 up to m0 plus d minus 2, which is 2 plus 3, which is 5. So it contains 2, 3, 4, 5, which is a string of 4 consecutive zeros. So it has these 4 consecutive zeros, and therefore the minimum distance is 1 more than the number of consecutive zeros. So it is actually 5. That also makes sense because your design distance is 5. But now, okay, why am I doing all this? Because I want to actually say that in this particular case you can actually determine what exactly is the null spectrum. Why is that? Well, look at the q cyclotomic cosets mod n. Look at the q cyclotomic cosets mod n. Now according to our definition, these cyclotomic cosets were the result of an equivalence relationship in which we defined A to be equivalent to B if and only if A was B times some power of q modulo n. But remember, since q is 1 mod n, any power of q is also 1 mod n. So, that means that A is equivalent to B if and only if A is equal to B. In other words, each equivalence class is a singleton set, it contains just a single element. There are no conjugates of an element other than itself. So, for in this particular case, when you look at the frequencies and try to partition them into the equivalence classes or cyclotomic cosets, you find that basically there are 15 cyclotomic cosets, each containing a single entry. Okay. Now, we have imposed the condition that the null spectrum contain the zeros 2, 3, 4 and 5. So, I have put that down here 2, 3, 4 and 5 I have included in the null spectrum, and now when we try to estimate the dimension of the code, we know that the dimension of the code is the number of frequencies that lie outside the null spectrum, which in this case is 15 minus 4 is 11. So, the minimum distance, the dimension of the code in this case is 11. Okay. So, in general, it is always going to be the case with Reed-Solomon codes that the cosets are singleton cosets, and therefore, when you mandate that a string of d minus 1 consecutive frequencies belong to the null spectrum, then the null spectrum can be tailored to contain exactly those frequencies and nothing more. So, the size of the null spectrum is d minus 1. So, the dimension of the code is the size of the complement of the null spectrum. So, it is n minus d minus 1. So, it is n minus d plus 1, and it turns out that this d is actually the minimum distance of the code, because by the way, since the minimum distance in general is larger, greater than or equal to d, this quantity is greater than or equal to n minus d min plus 1, since you are subtracting a potentially larger quantity. But remember that a code is maximum distance separable if k is equal to n minus d min plus 1. We stated that for the binary case, it extends to the non-binary case, and so in fact, because of the MDS condition, it turns out that not only do we have this bound, but this bound is in fact an equality, because the minimum distance cannot be any better than d, because if it were, then you would have something that exceeds the MDS bound. So, anyway, that I think went by a little quickly, but anyway, it turns out that this bound on the dimension of a Reed-Solomon code is always going to be tight, and so the minimum distance is the design distance, and thus the general parameters of any Reed-Solomon code are block length n, minimum distance d, and dimension n minus d plus 1, and hence they are always MDS, maximum distance separable. Okay, so, that was the second class of codes. So, we gave you a general definition of BCH codes and showed that binary primitive BCH codes and Reed-Solomon codes are examples, and from a practical point of view, these are very widely very much relevant, because both are used often in practice, and Reed-Solomon codes are the single code that is used the most in applications worldwide. Alright. So, now how do you decode BCH codes? So, now I am talking about BCH codes in general. So, that includes both primitive binary BCH codes as well as Reed-Solomon codes. Okay. So, we are going to talk about both classes of codes at the same time. Just a reminder, so what is the BCH code setting? You have q and you have block length, which is relatively prime to q. M is the order of q mod n as always. C is a cyclic code of block length n, so it is contained in here, and there is an element alpha in some extension field fq, meaning some field larger than fq that contains an nth root of unity or an element of order n. And then the null spectrum is mandated to contain a string of consecutive d minus 1 consecutive frequencies, namely these starting with m0. Now, we are going to decode over a channel which is modeled as follows. So, it is going to be modeled as an additive channel model, additive noise, in which here is your transmitted code word, this is the noise or the error vector that is added to it, and that is your received signal. So, this is the transmitted code word, this is your error vector, and this is the received signal. All right. Now, in our channel model, since our code is going to take on values from a finite field f q, these others also are assumed to take on. So, you can think of this channel as kind of a generalization of the binary symmetric channel. It is probably a query symmetric channel or something like that, but anyway we have this additive channel model, and we will also assume that the error vectors are such that a smaller number of non-zero values of the error is more likely than a larger value. Okay, so, you generally try to correct a certain number of errors up to a certain limit as always. All right. Now, what we are going to do, now consider that the transform of the received vector. So, r of t is the received vector here, and consider its transform, which is given by this expression. R hat lambda is the sum R t alpha to the lambda t, and now R t can be broken up into C t and E t, and this is C hat lambda, that is E hat lambda. So, that means now you know that the code, the transform of every code word regardless of which code word it is, the transform values are 0 for a consecutive set of frequencies, right, namely these ones. So, in this frequency window, R hat of lambda agrees with E hat of lambda, which means that the transform of the received signal is precisely the transform of the error signal in this window. So, what that means is that the null spectrum really gives you a small window through which you can peer at and look at the transform of the error signal, because it is clear that you have in this channel model you have access to the received signal. Your interest is in decoding the code word, but of course, if you know the error vector, then you also know the code word. So, decoding the code word is equivalent to decoding the error vector. So, in fact, our approach will be to try to actually determine what the error vector is. What handle do we have on the error vector? Well, we know that the error vector is more likely to have small Hamming weight than big Hamming weight, because we do not expect a lot of errors. We expect a handful of errors, not more than that. So, we are going to try to use that aspect of the error vector to actually determine it. And what this is telling you is that there is a small window in which I actually get to look at the transform of the error signal. So, now I have got two handles on the error vector. One, I know its transform for a certain range of frequencies. Two, I also know that it is most likely going to have small Hamming weight. I am going to put these two together and actually determine the error pattern from just a fragment. Okay. So, here is how you do it. Now, we have defined the term syndrome earlier. This is a slightly different definition of the syndrome. In fact, they are equivalent, but for the moment let us just say that it is an equivalent syndrome and leave it at that. So, we define a polynomial S of z, which is sigma r hat lambda plus m naught z to the lambda. So, this is kind of like a normalizing shift, lambda going from 0 to d minus 2. So, this is precisely the collection of frequencies for which you can evaluate r hat, for which the transform of the received signal equals the transform of the error vector. So, these are the frequencies lambda through m0 through m0 plus d minus 2, where you know the transform of the error vector. Now, it is convenient to set d minus 1 to be r. So, this r has nothing to do with the received signal, it is just a symbol. So, let us define d minus 1 to be r and define s infinity of z. Okay. Now, we already defined s of z. So, this is a different term, s infinity of z, whereas this is a polynomial, s infinity of z is actually a power series. So, it is worth noting that down here. This is actually a formal power series. Whereas this thing over here is a polynomial. So, they are two different entities. Now, also you might actually look at this and say, wait a minute, how is it that you are able to compute S infinity of z? After all, you only know E hat of lambda plus m 0 for lambda going from 0 to d minus 2. How can you actually set this to infinity? Well, we are aware of that. We are aware that you are not able to compute S infinity of z, nevertheless it aids in the analysis. Okay. How does that help? Well, we continue this. This is the sum, and then I am going to introduce the definition of E hat of lambda here. So, I replace this by this expression here, E hat lambda is E t alpha to the lambda t summed over t, and then I have the z lambda. I rewrite this and I do two things here. First of all, I am going to assume that let w be the number of errors, which means what? Which means that the number of symbols of the form E sub t which are non-zero is w. And furthermore, we will assume that the subscripts t for which E of t is non-zero are the ti. So, E of ti is non-zero for I ranging from 1 to w. Now, all the others are 0. So, in this really, although it looks like there are n terms in the summation, only w of these are non-zero. Okay. So, with that I am replacing this sum over these n values of t to the w values of I, and I have E of ti, and then correspondingly I bring the alpha to the lambda ti m0 ti term inside and take the summation on lambda inside. So, I have z to the lambda alpha to the t raised to the lambda. Now, this thing in the field of formal power series reduces to 1 minus 1 upon 1 minus z alpha to the ti. So, it is just like summing 1 plus z squared plus z cubed and so on, and you will end up getting 1 upon 1 minus z. So, in exactly the same way, if you keep summing these terms, what you will actually get is 1 upon 1 minus z alpha to the ti. Now, let us write that as omega of z by sigma of z. Let us just say that that is what it is. Where what is sigma of z? Sigma of z is nothing but the denominator once you put all of these on a common denominator, which is this. And because the ti appear in terms of the zeros of this polynomial is called the error locator polynomial. Notice that it has degree w. Similarly, if you actually work this out, you will find that omega of z is given by an expression like this. It is the sum I is equal to 1 to w E sub ti alpha to the m naught ti product j equal to 1 to w j not equal to I 1 minus alpha to the tj sigma. And you can see that if you divide this by sigma of z, you will get the term for omega by sigma that we had earlier. Okay. Now, because the E sub ti's appear here, this is called the error evaluator polynomial. And the point being that if you can determine sigma of z and omega of z, then you can actually find both the error locations as well as the error values. Okay. So, now our goal, our initial goal was to determine the transmitted code word, and then we said, you know what, determining the code word is the same as determining the error pattern that led to the received vector. And then we said, well, what I really am interested in is the error locator and the error evaluator polynomials, because if I know those, I can recover the error values and the error locations and correct the errors. Okay, so that is our goal. And as I pointed out, the degree of sigma of z is w, then which is the number of errors, and the degree of the error evaluator polynomial is 1 less than that. So, in terms of, since the number of errors is expected to be less than or equal to d minus 1 upon 2, w is less than or equal to r upon 2, because we defined d minus 1 to be r. Remember, d is equal to 2t plus 1, where t is the maximum number of errors you can correct. So, that is where I have derived this inequality from. And the degree of omega z is 1 minus this, so it is given by this expression. Okay, so now all of this is in terms of S infinity of z, but on the other hand I just pointed out that I do not have access to S infinity of z. So, you might ask, well, what is the use of this if you do not know what S infinity of z is? Well, that is true, but here is what we can do. What we can say, so replacing S infinity of z by S of z. So, here is S of z, and notice that it is equal to S infinity of z provided you go mod z to the r, which means that if you neglect terms in z to the r or higher, then there is no distinction between S of z and S infinity of z. Therefore, S of z is omega of z by sigma of z provided you restrict to modulo z to the r, or equivalently S of z is omega by sigma plus some polynomial times z to the r. Now, if you think about it, you are neglecting terms in z to the r and higher. So, this is a formal power series, however, there are no negative exponents of z in it. Okay. So, that is important to keep in mind. These are technicalities, by the way. So, if you some of one or two of these points goes past you, do not worry. I am just trying to be careful, a little bit careful here. So, this is a formal power series, however, there are no negative exponents of z that appear in this. Okay, so, now I am going to multiply through by sigma of z. So, then I have sigma of z S of z, which is a polynomial, because this is a polynomial, this is a polynomial, omega is a polynomial, and therefore, what I have on this side must be a polynomial. Okay. So, from that I get that sigma of z times S of z minus omega of z is this, and this must be a polynomial because these are polynomials. So, this must be a polynomial. Okay. Therefore, this entire thing must be a polynomial. Okay. It has only a finite number of terms simply because there are a finite number of terms here, and even to begin with there were no negative exponents of z. So, this had only positive exponents of z. So, that makes this a polynomial. So, now I can write omega of z is sigma of z S of z plus b of z times z to the r. Okay. And you can think of this, by the way, this equation here is often called the key equation of for decoding BCH codes. Right. Okay. Now, you look at this expression and say, you know what, this looks like I am trying to actually compute the GCD of z to the r and S of z, because I know that if I try to compute that using the extended Euclidean algorithm, then at the end I will end up with such an expression where this is the GCD. Okay. So, this suggests that maybe the Euclidean algorithm will, if carried out with starting with z to the r and S of z, maybe it will give us the sigma and omega, and that turns out to be true. Okay. That turns out to be true, although the proof is somewhat lengthy. The proof is somewhat lengthy, so I will actually skip that. All right. So, what we have actually done is that we have started, I have introduced the problem of trying to decode BCH codes, and I took you to a series of steps through the key equation to this point, and I said, you know, the Euclidean algorithm looks like it could handle it. Okay. Now, there is a gap to fill because I am not proving that the Euclidean algorithm can do it, but we really lack the time because that will take us several lectures which we do not have. So, now what I am going to do next is I am actually going to go through a complete decoding example with you and then show you how it actually works. Okay. So, the decoding example is here. So, here in this example the code is binary. So, Q is 2, the block length is 15, so m is 4. The multiplicative order of q mod 15 is 4, and let us say that the design distance of the code is this should have been 7. Let us say that the design distance of the code is 7, which means that this code is capable of correcting 3 errors, d minus 1 upon 2, which is 3 errors. So, this is in fact a triple error correcting BCH code. Okay, so, let us just make a note that this is triple error correcting. Okay, so, this is a triple error correcting code. Now, according to the BCH definition, and also we will assume that so this is BCH, it is primitive BCH. So, M0 is equal to 1. So, that means that in the case of this code, the mandated string of zeros or consecutive frequencies in the null spectrum is 1 through 6. Okay. So, we are saying now that the null spectrum of the code must contain this consecutive string of 6 frequencies. So, this is called a triple error correcting BCH code, and I have just written that here as well. Now, here are the cyclotomic cosets. The mandate is for you to pick these in the null spectrum. So, you want to pick 1, 2, 3, 4, 5 and 6, and you know that if something belongs to the null spectrum, then its conjugate must also appear in the null spectrum. So, because of that, you are forced to pick the null spectrum to be the union of these 3 cyclotomic cosets, that is 1, 2, 4, 8, 3, 6, 12, 9, 5, 10. So, you are forced to pick these 3, and this then is your null spectrum. The dimension of the code now you know is the size of the complement, which is 5. Now, we want to consider an example of decoding. Okay. So, in this example, so let us say suppose in a certain instance the received vector, so there was a transmitted code word, and let us say there was an error sequence which corrupted the transmitted code word. Suppose the received vector was 1 for t lying in this set 0, 3, 4, 5, 6, 7, 8, 12 and 13, and it was 0 otherwise. Now, we want to actually carry out decoding. The first step is compute r hat of lambda. Okay. For lambda, for the frequencies lying between m0 and m0 plus d minus 2. So, recall that here m0 is this is equal to 1 and this thing is equal to 6, okay, because this is 1 plus 7 minus 2, which is 6. So, you want to compute the transform for lambda ranging from 1 to 6. Okay, so, that is your range of interest. Now, since r of t is non-zero precisely for these at these time instants, that means that you have to actually compute this. So, supposing you want to compute this for therefore, r hat of 1. So, if you set lambda to be 1, that is you are computing it for the first frequency in this range, then that gives us alpha to the 0, 3, 4, 5, 6, 7, 8, 12, 13. You can use Horner's method to compute it. So, that is alpha 0 into 1 plus alpha 3, 1 plus alpha 4, alpha 5, alpha 6, alpha 7, alpha 8, alpha 12, alpha 13. Okay, so, this is Horner's method to actually compute this. So, 1 plus alpha is alpha 4, alpha 4 is alpha 8 plus 1 is alpha 2, alpha 2 alpha is alpha 3 plus 1 is alpha 14. Now, alpha 14 times alpha is alpha 15 plus 1 is 0. Okay. So, you are left with starting the computation from here again. So, that is 1 plus alpha, alpha to the 4, alpha to the 5, alpha to the 10, alpha to the 13 plus 1 is alpha to the 6. Okay. Now, in case you are wondering, well, how do you actually do this? Okay. So, let me just, so there is no mystery here, we went through this before. So, perhaps what I will do here is I will pull up the add1 table from a previous lecture. Okay, so here is the add1 table. So, what I am in using Horner's method, I have also used the add1 table for this finite field. So, I am going to assume here in the computations, I am going to assume that alpha 4 plus alpha plus 1 equals 0. Okay, that is, alpha is the primitive element in the particular finite field. Okay, recall that here we started with F2 and then we were led to F16, and in this larger field which we call the big field, alpha is an element of order 15. So, alpha is primitive, and because alpha is primitive, I can actually choose this to be the primitive element which we have used so often in the past. Okay. So, that is why I am using this, and this is the add1 table, and it is the add1 table that I am been using here. So, 1 plus alpha is alpha to the 4, and you can see that. Okay. All right. So, if you compute this, you will find that it is alpha to the 6. What that means is that r hat 1 has been computed and found to be alpha to the 6. R hat of 2 by conjugacy, okay, so this is by conjugacy. By conjugacy, r hat of 2 is r hat of 1 squared, which is alpha to the 12. R hat of 4 is r hat of 1 to the 4, which is alpha to the 9. R hat 3 is alpha to the 13. I have not shown this here, but it follows from direct computation. R hat 5 similarly alpha to the 5. R hat 6 is r hat 3 squared, alpha 13 squared, alpha to the 26, which is alpha to the 11. Okay. So, in this way we have actually computed the first 6 transform coefficients, and they evaluate to 6, alpha to the 6, alpha to the 12, alpha to the 9, alpha to the 13, alpha to the 5, and alpha to the 11. So, here are these coefficients and written out in that particular order: r hat 1, r hat 2, 3, 4, 5, 6. So, this is your syndrome. So, this first step is to second step is to compute the syndrome. And since it is cumbersome to spell this out and work with a polynomial like this, we will use shorthand and just write it like this. So, here I am getting rid of the z's and just putting down the coefficients. So, alpha 6, alpha 12, alpha 13, alpha 9, alpha 5, alpha 11. All right. Now, what we do is we want to use the Euclidean algorithm, right, and we are going to pretend, right, we are going to pretend that we want to compute the GCD of z to the r and s of z, and we already have s of z here. So, here is s of z and here is z to the r is 6 in our case. So, the Euclidean algorithm says that you divide this by this and put down the remainder here, and that is your quotient. Okay. So, now I have carried this computation out on the side. So, let us take a look at that. So, here is z to the 6 in short form notation, and here is s of z, and we want to divide this by this. So, this is alpha to the 15. So, it is alpha to the 4, which will give you 1, alpha to the 9, 13, alpha squared, alpha to the 10. You subtract, you get this row, You look at alpha to the 9 and alpha to the 11, so that must be alpha to the 13, because that gives you alpha to the 24, which is alpha 9. And then you add again, and again here I need to use the add 1 table. For example, alpha cubed plus alpha 13, right. So, alpha cubed plus alpha 13 is alpha cubed into 1 plus alpha to the 10, which is alpha cubed into alpha to the 5, which is alpha to the 8. After you use this after you work with the odd 1 table for a while, you will soon learn it by heart. So, you will be able to do it automatically just as I did it here. Okay. So, that is how the alpha 8 came here. Similarly, this is 12, this is 6, 0, alpha to the 4. So, this is your remainder now, 8, 12, 6, 0, 4. So, here is your remainder, and the quotient was alpha 4, alpha 13. Now, in the Euclidean algorithm, you have to treat this like an Excel spreadsheet, and whatever you do here, you must replicate here. Now, it turns out that this column is really, we do not really care what happens in it, because it turns out that it is not material to our calculations. So, I will just erase that, and we will focus only on replicating the calculation that gave us this here. So, to get this entry, we took this, multiplied it by this, and subtracted from this. So, we get this by subtracting from this times this, that gives us this. So, this stands for the polynomial alpha to the 13 plus alpha to the 4 z. Next, we divide this by this and take the remainder. Okay. And that computation is carried out here. Okay. I will just let you look at it, and as you look at it, I will also check that the computations are correct. So, this looks okay. So, this is our new remainder, and that is our new quotient. So, in this table we put down the quotient here and your new remainder there. Yeah, even that looks okay. So, we get back here, and now we need again to pretend that it is an Excel table. So, we got this by multiplying, by taking this and subtracting the product of these two from this. So, we get this by subtracting the product of these two from this. So, that will give us alpha 7, alpha 11, 0. Okay. And even that computation where we multiply these two and add 1, I have done this a little later. So, here we go. So, I have alpha 14. So, we multiply and add 1. And again the computation looks okay. So, this seems correct. So, we should have alpha 7, alpha 11 in the table, alpha 7, alpha 11, 0, alpha 7, alpha 11, 0. And now you divide this by this to get this remainder. So, here is our last division. This again looks correct. So, we are left with a remainder of this quantity here. Now, of course, one question in your mind is, should I keep going on forever, or is there a stopping point? And it turns out there is a stopping point. What is the stopping point? You stop. So, let me to just make this clear, let me copy this page, okay, and where I can Okay, so here's this page and I now have room to make some put some markings on it. Okay. So here if you keep track of the degree, so what's happening here is that you are getting possible candidates for omega of z. Okay. So now the degree, let us keep a track of the degree of these entries. This is 6, this is 5, this is 4, this is 3, this is 2. On the other hand, we said that the degree of omega of z is equal to r over 2 minus 1, which in our case is 6 over 2 minus 1, which is 2. So, what we are actually looking for is the first instance when the degree is either 2 or less than 2. So, you notice that this is the first instance at which the degree of this of the polynomial in the leftmost column is 2 or less than 2. So, the moment you see is that you draw a circle, what it turns out is that the polynomial that you get here is not perhaps omega of z, but it is a constant times omega of z. Now, again I am not proving the theory, you can actually read the book by McWilliams and Sloan which goes through this. It is a somewhat lengthy proof, it will take a lecture or two alone to prove that. So, this is our stopping point. Our stopping point is you look for when the degree in the leftmost column dips to 2 or less, that is r by 2 minus 1 or less. Okay, so, that is what happened here. The degree dipped over here and then we actually said okay, this is some constant times omega of z and this is some constant times sigma of z. Remember we said that z of r times something plus s of z times something was giving you omega of z. So, now you know sigma and omega up to a constant. Okay, how do you figure out that constant? That is easy, because what you know is that, so here is your this is some now okay, another point here to be made here is that in this table what we actually got is omega of z and this is sigma of z. Now, in the non-binary case you need to find the error locations as well as their error values. In the binary case, once you know the error locations, then you know the error values, because the error values can only take on the value 1. So, in the binary case, as in this example, it suffices to determine sigma of z. Okay. So, now our focus is on this particular polynomial of degree 3, which is sigma of z. Now, what we know is that this polynomial may not be sigma of z, but it is sigma of z up to some constant multiplication. Now, you look at this and say the constant term here is 1. So, if I have to make this constant term 1, I would have to multiply this entire polynomial by alpha squared. So, that is what you do. You multiply this entire candidate for sigma z by alpha squared and you get z cubed alpha cubed plus z squared alpha to the 7 plus alpha 6 z plus 1. This is now, this is then your true error locator polynomial. This is the error locator polynomial. Okay. And now all you have to do is factor it. The next step is to factor it. Okay. So, in terms of the steps, I guess we had step 2 was to compute this. This Euclidean algorithm is step 3. It is the Euclidean division algorithm. Okay. And then once you found this, you could call this scaling step 4, and finally what you do is you find you try to find the zeros of this polynomial and you do something that is called Chien search. There are alternatives, but for now let us just we will search by just checking all the elements in the finite field to see if it is a 0. For example, if you set z to be 1 here, you will notice that it is alpha cubed plus alpha 7 plus alpha 6 plus 1, which turns to evaluate to alpha to the 11 and is therefore not 0. So, you then try z equal to alpha and then z equal to alpha squared. It turns out that at alpha squared, okay, so you plug in alpha z equal to alpha squared, here you get z cubed alpha to cube alpha to the 6 alpha cubed plus alpha to the 4 alpha 7 and so on. Okay. So, you get this polynomial, you evaluate this using Horner's method and you find that it is equal to 0. Okay. And so, z equals alpha squared is a 0. Similarly, it turns out that this polynomial here has the 3 zeros alpha squared, alpha 11, alpha to the 14. And you can see from the way this is actually structured that the error locations are the correspond to the, so the error locations are not the reciprocals, but rather correspond to the reciprocals. So, the reciprocals being alpha to the minus 2, alpha to the minus 11, alpha to the minus 14, which is alpha 13, alpha 4 and alpha. So, that means that the error locations were actually, so there were 3 error locations and these are the 3 error locations. So, we have actually successfully decoded the code. Okay. Now, in the non-binary case, you would actually have to use partial fractions and the error evaluator polynomial to then determine the error values, but we will not actually go through that. Okay. So, that actually is more or less all that I wanted to cover today, and that also finishes our course for us. So, I think what we have basically done in this course is it took us some time because I first went through the basics of error correcting codes and then I took you to the GDL, which I feel is important in its own right. We did block and convolution codes, then we did the GDL, and then we applied it to understand LDPC codes, which is the modern class of codes, and then we came back and did the classical codes, Reed-Solomon codes, and so that took us some time, but hopefully you have benefited from that. Now, what I will do is what we will do at this end is have these lecture notes made available and possibly some homework sets as well. Okay. So, with that, I wish you the best. It has been an interesting and enjoyable experience. I hope you find this useful. So, thank you. I think I would like to end by actually thanking the staff here at IISc. The staff here have been excellent, ranging from Professor Gopakumar, who was really very encouraging right from the start and motivated, I think, the bulk of the faculty of IISc to sign on here, as well as the local staff here, Mr. Singh here, A.K. Singh, as well as the assistants here. They have been very helpful and I would like to also thank them. Okay, so, with that I would like to close.